Let's look at applications. We have software as a service, which is how we're going to deliver our application. The browser will access the application. The software as a service is built of services. Some of those services interact with the client by delivering the results of a computation of the client, but most of the services actually interact with other services. And they're linked together by workflow. And of course, the software service, we already looked at the basic Web 2.0 cloud companies, the social networking, the photo sharing, Wikipedia, the file systems such as Live Mesh and MobileMe and Google Docs and Office Live and things like that. Mathematica and MATLAB offer science tools with cloud backends. Geographical information systems, Google Earth and Microsoft Virtual Earth, are also important software as a service applications. Google Maps is, if you like, an elementary version of Google Earth. These are some rather old success stories, things that people were able to do dynamically because there were clouds. They did not have to buy their own computer center. And they were able, here's a company scaling from 25K to 750K customers in 1 week, which was 40 servers to 500 servers. And they just needed a credit card, which is of course not trivial, but they did not have to hire people and do things like that. Eli Lilly, where uses Amazon Cloud as a backup to their own high-performance computing cluster. So when they run out of space on that, they go and run on the spot market on Amazon. Here's some more success stories. It actually repeats the New York Times case. We have a photo storage application, and it is all built on Amazon. And I already mentioned an even more obvious one is Netflix is entirely built on Amazon. And so we have plenty of success stories. They're all probably a little anecdotal because we don't have a systematic analysis of the cost benefits and the glitches they had. But and this company called Animoto had a Mother's Day increase in need, and they were able to do a ramp up of a factor of 10 in users in 3 days. This, of course, is a big change from the beginning of the internet in 2000. In fact, you can say this is connected to somehow problems that companies like Sun had. The Sun flourished in around 2000 because every internet company had to buy their own Sun internet servers. Now, nobody has to do that. You just go and get your credit card from your venture, feed it with money from your venture capitalists, and then you just do it all on Amazon or Google or Azure or something, or some other system which might even be cheaper. If we want to look at what it takes to bring applications to the cloud, we need to think carefully how to do this. We need to worry about fault tolerance issues and performance issues, and it's always quite difficult to do this. But there aren't actually drastic differences between clouds and traditional clusters, except possibly in the performance area. Clusters probably cost more, but they actually do provide more clearly high performance. This slide here gives a list of what applications work on clouds. At the moment, there's actually little science use of clouds. It's really quite modest. I apologize for misspelling biology here, but I noted that, or we already noted that Lilly, which is an Indianapolis company, uses commercial clouds for large-scale chemistry computations, but the IU chemistry and biology departments do not. In general, life sciences is a big user of clouds because they have new applications, so they do not have traditional implementations that which are already set up on HPC, Also, they don't have the large-scale simulations requiring the low latency communication that supercomputers have. A nice example is Venus C, which is an Azure project in Europe, which supported successfully 27 applications, which were all done using very straightforward technology, using a generalization of what's called the worker node on Azure, which is a particular machine image optimized to being a worker. A worker is a part of a so-called master worker compute model where you have a master controller and that stores a list of work to be done, and you have workers who diligently do the work. When they finish their work, they come back to the master to see what else needs to be done. So these are so-called pleasingly parallel applications, which are the simplest things to put on clouds. Large numbers of problems fall into that type. All the sensor-related problems are of that type. The long tail of science is of that type. An important class which is not so easy to put on clouds is actually data analytics, and that's critical because this is a big data class we're doing, so we better know that data analytics runs on clouds. Sort of obvious it does because Facebook, Google, Bing, etc. are large-scale data analysis problems, and they all run on clouds. There's an issue which we've already mentioned about iterative variants of iteration needed inside data analytics, and that needs extensions of things like MapReduce to support iteration. Here are the 27 Venus C applications. We have set of biology ones here, civil protection, physics, more biology here, medicine. So this is all, these ones here are all biology related. Here we have chemistry, which is, it says molecular docking and drug discovery. Those are actually biochemistry. We have architecture here and civil engineering. One interesting service was for estimating the energy efficiency of buildings with a cloud service. Seismic propagation in earth science. Here we have some computer science or computer technology type applications, computational algebra. We have in the area of risk estimation, doing fast simulations and things like that is an important area where you can imagine expanded use of clouds. Here we have basic aerospace. There's not so much here because remember the simulations that will be used in a lot of aerospace computations currently don't run so well on clouds because they require low latency communication.